Welcome to the Ottobock Experts on Demand education series. In this previously recorded webinar, Aideen Curran and Dr. Jerry Stark will introduce you to the L.A.S.A.R Posture 3D. You'll learn how the sophisticated digital alignment tool can help you objectively measure the location and direction of ground reaction forces and the consequential effect on a prosthesis or orthosis. This course is approved by ABC for 1.25 CEU credits. Please note that in order to receive credit, you're required to take the quiz and pass with a minimum score of 80%. The quiz link can be found on our Experts on Demand webpage or in the YouTube video description below. Enjoy the webinar.
Okay, so today's topic is how the L.A.S.A.R Posture 3D can help you find objectivity in alignment. And what we're going to go through today is who you can use the L.A.S.A.R posture with, what the L.A.S.A.R Posture 3D actually is, when you would use the L.A.S.A.R Posture 3D in your treatment cycle, where can you use it, and the most important thing, why should you use the L.A.S.A.R Posture 3D, and then simply how we actually use it. So first of all, who can benefit from the L.A.S.A.R Posture 3D? So what's really great about this device is that you can use it for any prosthetic or orthotic end user. So this can be anything from a simple foot orthotic all the way up to a hip disarticulation prosthesis, and obviously everything else in between. In fact, I'm going to go one step earlier and say that you can actually use it for any sort of positional casting. So for example, if you wanted to take a weight-bearing cast to make a partial foot prosthesis and you wanted to know the exact angle of the ankle joint, you can actually use it there as well. If you are both a prosthetist and an orthotist, you're going to get double value out of this device. So what is the L.A.S.A.R Posture 3D? So it's probably worth mentioning that there is actually two L.A.S.A.R postures. It was our very first original L.A.S.A.R posture, and this particular one was produced over 20 years ago now. So despite having an old version and a new version, the L.A.S.A.R posture is essentially a measuring device that's intended for verifying and optimizing the static alignment of both a prosthesis and an orthosis together with the patient in the device. And that's a really important point. The original version, as you can see on the screen here, let me see if I can get my little laser pointer. Okay, so what you'll see here is a very large force plate. And then we have this small compensation plate to the side. So as the patient was standing on the force plate, there's 4 cells in here. They had their affected side on the force plate and then their sound side or contralateral side in this case on the small compensation plate here. So that force sensing platform had a projection system. So it had a laser projection, if you can see this small little red laser here, and this is what is projected onto the patient. So what you can see from this, the information you're getting is the center of pressure of the foot, and then it's projecting what would be the vertical component of the ground reaction force. So only the affected side, the center of pressure, and the vertical component. Now, you might think it's my strange Australian accent that I'm using the term L.A.S.A.R posture, but in fact, it's an acronym. So it stands for Laser Assisted Static Alignment Reference. In other words, we have this reference line that's depicted by a laser in this case, and it's going to assist us during static alignment. So the 3D version, so we released this probably about 2.5 years ago now, and it's based on a very similar technology, but we've implemented a few more things to really get the advantage out of measuring ground reaction forces. So this is the L.A.S.A.R posture 3D. Again, we have a force plate, but you can see this time the force plate is separated out into the two limbs. So we still have the 4 cells, but now we can measure both the sound side and the affected side at the same time. We also have 2 camera stands. So these poles here are actually sets of cameras. And if you can see, there's some very, very small little circles in these camera poles here. Now, they are the cameras facing, in this respect, it will be the coronal plane camera. And here we have the sagittal plane camera. So you're capturing the image, and this time, instead of projecting a physical laser onto the body, we have a tablet that comes with the system, and it actually captures a real-time image of the patient. So whilst obviously this picture here is a still, it actually looks like a video. So it's in real time, and it projects the ground reaction force on both limbs. So inside the case here as well, there's a little mini computer, and that's obviously what's processing all this information. And you get these 2, well, it's 1 case, beg your pardon, that's the lid, that's the larger case. And you get this case for it to be easily transportable. However, the system is actually designed, if you were to use it in your clinic, it's designed to just use the force plate and the 2 camera poles. And so you don't need this large case, okay? You can actually wall mount these cameras. We sell little wall mount clips, and the cameras just click into there. So in terms of, how much space or how much footprint is the device taking up, it's really only the force plate down the bottom there. So again, that's what it looks like. So the person is standing on the force plate with the cameras pointing in each direction. And then you're actually seeing, so these are images taken from the tablet screen. You're seeing the patient's body, and you're seeing the ground reaction force from both legs at the same time. And you're seeing the 3D ground reaction force. So that's the biggest difference between the old version and the new version, is that it's not just showing the vertical component, it also shows the horizontal influence. And so what we're getting here is actually the resultant force. So with the patient standing there on that force measurement plate, the vertical and horizontal ground reaction forces, as well as the torsion moments, are actually being measured. So that information is getting sent to the little mini computer. That's via Wi-Fi. And then the tablet is actually displaying that data overlaid onto the image of the patient. So you'll see that one line is green, that will be one limb. One line is blue, that will be the other limb, which is very easy to see here on the coronal plane. But when you look at the sagittal plane, it looks like they're overlapping. And in fact, they are. So we have natural stance here. This person has got no affected limbs. And you're seeing here that the 2 ground reaction forces are meeting at the same place, at the same center of pressure at the foot, and they are essentially overlapping. And this is sort of ideal alignment that we're trying to achieve.
You can even see in that previous slide, Aideen, how the patient's resting on the ligaments of Bigelow at the hip. So he's actually pulling back in hyperlordosis. So even though that's a very typical non-involved patient or person, you can see that the laser posture tells us quite a bit with the vectors, right? It's not just the center of pressure, just to reinforce what you said.
Exactly, yeah. So when is the L.A.S.A.R posture 3D used? So in prosthetics, we're very familiar with 3 stages of alignment. So Our bench alignment is when we are establishing a pure relationship between the socket and the foot. And we would recommend that you always follow the manufacturer's guidelines for your bench alignment, because the manufacturer knows how best to set up the foot or the knee, whatever case it might be, depending on how it's designed. We take into consideration things like heel and forefoot levers, the material, all sorts of things. So please follow the bench alignment guidelines from the manufacturer. I'm not going to go into too much detail about bench alignment. What I will do is provide you with these posters here in a PDF format of transtibial and transfemoral alignment for you to look at later. But one thing that I always find very interesting is the concept or the conversation around which way the pylon should lean. And this is actually quite a funny little picture here that my colleagues back in Australia did. You think that we do everything upside down? Well, we do. And here is a bench alignment and a standing alignment of a patient who certainly does not have their pylon vertical or leaning in a particular fashion. And this is something that, I want for us to sort of break that mold and that thinking that the pylon needs to be in a certain way. What's really important is that we're maintaining the relationship between the socket. So you can see here the little dotted line is the alignment reference line passing down through to the center of the foot. So it doesn't matter which way the pylon is leaning, as long as the forces are being transferred at the correct place. So when we go on to static alignment, so this next stage, this is really where the L.A.S.A.R posture comes into play. So here we're actually measuring forces. And what's important about this stage is that we are now testing our bench alignment with the characteristics that the patient is putting into the prosthesis. So, for example, I'm 5'2" on a good day. I'm about 50 kilos. I'm going to, place my weight into my prosthesis very differently to someone who is 6'2" and 120 kilos. So this is where static alignment, is really important. It's that combination of the bench alignment, so just an entry sort of level alignment with the characteristics that that patient brings in. And it incorporates, the deficits that the patient has or muscle weaknesses and things like that, or contractures, whatever it might be. And then we go to dynamic alignment. And dynamic alignment is still important. It is still our subjective gait analysis, and we still spend time here. But for today's focus, we're really concentrating on static alignment. And that's just a little bit, from a prosthetics perspective. For orthotics, it's going to be slightly different. We don't have a bench alignment. So we are assessing our patient, and then depending on, what we find, we're going to then design a device. So we're going to decide whether the patient needs an AFO or a GRAFO or a KFO, whatever it might be. And then we're going to design this with the appropriate position of the shells, whether they need anterior, posterior shells, or where the joints or what type of joints they need. And then when we're applying this
orthotic, the thing is, like for orthotics, you don't really have an onboard documentation like you do in prosthetics. So it's nice to know where the optimal alignment is. You can't necessarily achieve it, but with 3-point pressure systems, you can see how close you are.
Yeah, exactly. So when we're applying the device, then we know that, for a situation like this, we know exactly the type of device, but we're trying to achieve an optimal position of that device or an optimal correction. And like you said, Jerry, we might not be able to achieve that, but we certainly know what we're aiming for. And that's when we would use the L.A.S.A.R posture. Where? Well, this is a pretty easy one. You can bring it anywhere with you. So like I mentioned, it comes in that little case here, but it is designed to be permanently set up in a clinic. Again, you can just wall mount these little poles and then get rid of the big cases. So why should you use the L.A.S.A.R Posture 3D? And I think this is, why you've all come here today to the webinar is, we're talking about finding objectivity in alignment. So, what does this really mean? Without objectivity, so without a way of measuring, we're really making kind of an educated guess. And we know that forces are not visible to our eyes. You can see here in my picture, planes fall from the sky and little Jane next door breaks her wrist. And the problem here is there is a force at play. Obviously, it's gravity. Now, we can't see gravity. I can't look outside my my window and see gravity. But we certainly know that gravity has a huge effect on a body. And it's the same with ground reaction forces. We can't see them with the naked eye, but we certainly know that ground reaction forces can affect a joint or the movement of a joint. And so we use visible landmarks, so anatomical landmarks, to help us locate the joints on the body. But the hidden things that we can't see are the ground reaction forces, the levers and the torques that are acting. And it's really, really important. These hidden values that we can't see are really the difference between safety in a prosthesis or an orthosis versus dynamics, or actually really finding that nice balance between safety and dynamics. Ground reaction forces can help us distinguish what a tiring situation is from someone who's standing quite comfortably. We can identify abnormal stresses on the tissues and the joints. So we're finding objectivity by using science. So the L.A.S.A.R posture really is based on Newton's third law. For every action, there is an equal and opposite reaction. So I'm taking you back to Physics 101. As you can see here, we have our transfemoral user has a force acting into the ground, and you'll see an equal and opposite force, our ground reaction force, in return. Now, what's important that we obviously know is that there is a vertical and horizontal component of that force. So if I take you back to L.A.S.A.R posture and how we're measuring with the 2D version, so the older version, it was measuring the center of pressure at the foot and projected the vertical component of the ground reaction force. But what's really neat about the 3D version is it actually shows you that resultant force. So you can see both the vertical and horizontal components. And this is exactly what we are measuring here, and what we're aiming for really is this quiet standing. So I'll talk a little bit about quiet standing in a second. But here
that shear is really important, not to interrupt you, Aideen, but that shear that you showed on the previous slide, that's really important for you in transfemoral, because that's indicative of what you're achieving at heel strike. So that shear at the point of contact at the floor tells us a lot about how that device is acting. And that's also, it can also preserve stability or cause it to become unstable.
Yeah, thank you, Jerry. So for practical application in prosthetics and orthotics, when we have a look at the averages of healthy subjects, it can be really helpful. So these results here are from a peer-reviewed study in 2018 by Bellman. So he got a group of 50 neurologically and orthopedically unremarkable subjects, and he examined them for sort of a standardized baseline situation. The results were average for both legs, resulting in mean values for 100 limbs. And this is the results plus or minus a few millimeters of what a normal, I'm doing air quotes here, physiological alignment looks like. Before I get into it in too much detail, this isn't the first time that this type of study has been done. Way back when, 20 years ago, with the first L.A.S.A.R posture, a similar study was done by Professor Blumentritt, and the results are the same. The human body hasn't changed over the last 20 years. And so these ground reaction forces are positioned in normal, quiet standing at particular points related to the joint. So if we have a look at the greater trochanter, you'll see that the force lines, so the ground reaction forces, are posterior to the joint. So that's creating an extension moment at the hip. With the knee joint, you'll see that the ground reaction forces are anterior to the knee axis, and this is called the compromised axis of rotation. I'll get into that maybe a little bit later on, but essentially it's a way of determining where our compromised axis is. So it's a little bit anterior to that. And then when we measure from the lateral malleoli, it will be approximately 50 to 60 mil anterior to that. And also in the frontal plane as well, you'll see these approximate places at ASIS in relation to the center of the knee joint and the ankle. So this is what quiet standing looks like, or where the ground reaction force is in relation to the different joints during quiet standing. So what do I mean by quiet standing? So Jacqueline Perry described this, and it's when a person is positioned in natural stance, they have a quieter EMG. Okay, so particularly in the proximal muscles of the lower extremity. As we see here, natural stance occurs when the patient's center of gravity is over the center of pressure. So when they're in this position, they're going to get minimal EMG activity in the hamstrings, quads, hip flexors, or extensors. So really the only energy expenditure is occurring at the plantar flexors and dorsiflexors. What happens when you don't have those plantar flexors and dorsiflexors, or if they're compromised in some way? And this is where alignment comes into play. We need to position or get the correct relationships in order for us to achieve stability and to also be able to achieve this quiet standing. So we're not putting any undue forces or pressures on the body. And what I think is really important to sometimes reflect when we're talking about why we should be doing these things. And I always ask, what's the primary consideration of intervention? And for us as healthcare workers, it really is to do no harm. And we're quite familiar with following best practice standards. We have certain benchmarking in our industry. We use evidence-based practice. This has become paramount, particularly when you're discussing payer sources. And we use ISO quality assurance procedures. So as a clinician, we must be able to objectively validate our intervention. So I want to ask you that question, and you don't have to answer it today, but maybe something you can take home and think about. When we're talking about alignment, how do you validate your intervention? And that's what I think is, for me, the most appealing thing about the L.A.S.A.R Posture 3D is that it's a device that is within our reach economically. I know I can quietly hear some people snicker in the background, but truly it is economical. When you compare it to something like a Vicon video lab force plates, it is within our reach in our industry, but it's also within our comprehension. It doesn't require any interventions or interpretation from engineers or biomechanists. It's really using ground reaction forces. And it's also within our scope of time with our patients. So it should be really easy to implement this device and make it part of your treatment plan. And therefore, I see it really as an accessible technology to help us validate our intervention and provide objectivity in alignment. I personally use this device on absolutely everyone that I see, and I have done since 2011 when I first started using it. And I can truly say it reduces the time that you spend with your patients because it's taking away that guesswork. And it's also reconfirming sometimes when you know you have done the right alignment. And it can reduce the number of follow-up appointments as well because you're just getting closer to the best alignment much quicker. So how do we use the L.A.S.A.R posture? So hopefully some of you have watched my short little 10-minute preview video. I promise you I will record it in a more professional manner when we get back to the office. So I just wanted to point out a couple of things here on the screen. So this is like an animation of what the tablet looks like. So the very, very top button here, this little camera eye button, what this does when you're looking in the coronal plane, it will project a vertical line, and I'll speak about that in a second, for you to check the leg length, or if there's a leg length discrepancy, or if your prosthesis is too long, too short. You can press on that button and you will get that view from the camera. The second little eye down here, this button is going to change between the coronal plane camera and the sagittal plane camera. So you don't need the patient to be moving around on the force plate. So there's no safety issues there with the patient having to shuffle around. You can easily switch between cameras. The small little person icon here, really where you can go to create a patient profile. So you can put as much or as little information as you like about the patient in there. It can be as simple as a name, but you can actually capture screenshots, which is this camera icon there. You can capture a screenshot of what you're seeing on the tablet. So if you wanted to record or document your process, you can actually save each screenshot into the patient's profile. I think this is fantastic because you can have a patient who walks in and they're saying, you know, I'm experiencing pain, and you have put the device on, whether it be an orthosis or a prosthesis, or they're complaining that the knee keeps yielding. So you can take a before photo and then you can pop that in their file. You can do your intervention and then you can take another screenshot and then you can show side by side and you can annotate the screenshot and say, here's before, here's after, we had pain, no pain, etc. I think that's a really, really valuable tool to document this as well. The 3D little icon here, you can actually toggle between 2D. We call this legacy mode, which is like the old L.A.S.A.R posture with the red laser line, or you can have 3D, which will give you your resultant forces. We also have a little information button here. Fantastic. It actually has little video tutorials in there. So if you're not really familiar with sort of how you would go through step by step with the alignment, you can actually follow these short little tutorials. There's a transtibial and a transfemoral. I don't believe there is an orthotic one in there yet. My apologies. And it also has our alignment posters and also the IFU, so the information for use. So you'll be able to see all sorts of information in there, how to set it up, how to use it, how to problem solve, troubleshooting, things like that.
It's really your own portable little, gait analysis lab, right? So as you mentioned, Aideen, you might pay $150,000, $200,000 for an 8-camera dual force plate Vicon system, but with this one, you're getting exactly what you need, and it was made for prosthetics and orthotics.
Actually, that's a really great point. Thanks, Jerry. I've never thought of that, to be honest. Yeah. So the little icons down the bottom here, these are actually measuring torsion. So you can see they're in Newton meters. I'll get to that in a second. And then down the bottom, it shows you body weight as well. Some other little features, if you're struggling to see, you can actually just pinch the screen and zoom in. Again, you can take little photos with the zoomed in image there as well. So some features of how we can actually use it. The first thing that I always look at is down the bottom at the body weight. So if you see down here, it separates between each side, and you can actually see the patient's body weight in kilos, pounds, and as a percentage. If you have a look down the bottom here, these are red. So it's telling us that the patient isn't sufficiently loading the legs equally. And once they are, it will illuminate green again. So I think this is really great because it's not often that we have our patients, standing in their device and for us to truly know how much weight they're putting through. So this can be an indication. Are they having socket pain, or are the trim lines of my orthosis causing me not to load my device? Is my prosthesis too long or too short? Other things that can be an indication of not loading their body weight through it. So, for example, they don't feel safe. And I had a colleague or a customer actually describe a really interesting situation where she actually used this specific thing with the L.A.S.A.R posture to have an approval or part of an approval for a microprocessor knee. So the patient was coming in saying that they felt unsafe and didn't want to load their prosthesis. It was a mechanical knee, and she was able to provide photos like this and evidence, real objective information to show that the patient wasn't loading their prosthesis. They organised a trial of a microprocessor knee, and he felt a lot, safer, more comfortable. And then again, she was measuring him each time, and you could see the load had changed. He finally felt safe to put load through the prosthesis and trust it. And so she actually used this as part of her documentation, and I thought that was a really cool story. So that's the first thing, is measuring body weight. The second thing you can see here is that it measures torsion. So you will always have a certain amount of torsion being registered here, but what you want to be looking for is that one side is no more than 2 Newton meters more than the other side. And the little arrows will depict whether it's going to be internal or external rotation.
This is a really great feature for orthotics, by the way, because of the triplanar nature of the foot, right? It's great for prosthetics, frankly, too, but also when you're talking about AFO design. You don't get this from anywhere else, that you could sense torque.
Yeah. I think that's why it's just so great if someone is working in both prosthetics and orthotics. You just get so much value out of this tool in so many different ways. The next thing you can use it for is for a leg length discrepancy, or if you're trying to establish the correct length of a prosthetic device as well. So often we know that our patient has a leg length discrepancy, but, exactly by how much, a feeling is one thing, but to be able to actually measure it here, I think is really nice. I know I've certainly had, conversations with patients about, the prosthesis being short. And then this is a way of me really showing them, what that effect has on their spine. So like I mentioned previously, where you can click on the camera button and show in the coronal plane a vertical line. So it's going to project a vertical line on the image of the patient. And if there is a difference, you're going to see that the vertebrae is not lining up through the center of that line. And that's what we want to achieve. So a really nice thing there for leg length discrepancies. We're going to go through a couple of little examples for both prosthetics and orthotics. If we don't get through them all, don't worry, you'll be provided this presentation so you can have a look at some of the examples there a bit later on, but I think we will have time. So I'm just going to talk a little bit about sagittal plane for prosthetics. So some of the examples that you might see with the patient standing on the L.A.S.A.R posture, there's several ways of using the L.A.S.A.R posture, and quite frankly, it's really difficult to describe everything via a presentation from my home office here. I absolutely love getting this in front of people and getting everyone to have a stand on it and have a look at their alignment before we get the patient on there. So we'll go through just a couple of examples. So here, what you're seeing on each part is, on one side, you're seeing the 3D L.A.S.A.R posture, and just for reference, on the other image, you're seeing what the 2D would show you. So the solid line and the green line is this gentleman's left leg here, and the blue line and the dotted red line are the contralateral side. So in this situation here, we don't have optimal alignment because we can see that the forces here the center of pressure are not at the same place at the foot. So there's a separation here. So we can see that the ground reaction force on this left side is slightly anterior. We really want this in the middle of the foot. We want a nice equal heel and forefoot lever. And so a simple way for me to get that ground reaction force more posterior would be an easy dorsiflexion of the foot. Okay, so that's a very simple one. This is quite common, especially once we've established our bench alignment. Normally at Ottobock, when we do bench alignment, we put an extra 5 millimeters under the heel of the prostheses. And what this does is slightly plantarflexes the foot. So when the patient stands in a static situation for the first time, that plantarflex foot is going to create an extension moment at the knee. And this is purely for safety. We just want to make sure that when the patient stands for the first time in their prostheses, that it's not going to collapse on them. So often when you come straight from bench alignment, you might have this little situation here, very easily solved by a little alignment change. This one's also a very interesting one, probably one of my favorites that I see when I'm helping people out and about in the field. Now you can see it's slightly different. So the V is in one direction in this example, and it's in the opposite direction here. So what you're seeing here is the center of pressure is at the same place at the foot, but there is a very big difference when it comes up to the hip. And that's because there is a moment acting about the hip here. And this is evident of when we have not incorporated a hip flexion contracture into our prosthetic alignment here. So whilst everything else appears to be okay, and this is the limitation here of the 2D L.A.S.A.R posture, that it appears to be at the center of the foot and at an okay place at the knee, but we weren't able to see the influence of that hip moment when we were using the 2D. So this is brilliant here that we can now actually see that, and then we can flex the socket accordingly.
You really wouldn't see any of these with the plumb line. So this slide really shows you wouldn't see any of these discrepancies with the plumb line, which just shows you position.
Mm-hmm. Yeah. And here is another example as well. Here it's actually a combination of both of these. So if I was to slightly dorsiflex the foot, I would also have to address the hip as well. So what we're aiming for is this standing relaxed position here. So this is when the two lines are meeting at the center of the foot. They are parallel and they are almost on top of each other. And a lot of people ask me, how perfect does it have to be? As close as possible, but often there are times where we can't get it on top of each other, but as close as possible, and most importantly, parallel. Another really nice thing in the sagittal plane that the device is able to show us is it has a really nice little quick start guide on the position, or the AP position, that our knee joint needs to be in relation to the ground reaction force. So we have defined very specific measurement from the knee axis to the ground reaction force. These are the 2D measurements here, and now that we have our 3D L.A.S.A.R posture, we've upgraded or updated the measurements of where that knee axis needs to be in relation to it. So if you can't remember, there's a really cute little quick guide in there. You swipe the screen down, you select your knee joint, and it will actually have it will actually display where the knee axis should be, and then the ground reaction force, so you can see how far away or how much you need to optimize that. In the frontal plane, so again, this was a little bit of a limitation of the 2D version. When we're just seeing that vertical component, we can't see the influence of the horizontal. So was it okay? Not sure. But here are two examples of what it actually could look like when you throw it into that 3D mode. So you can see here that despite being at the center of pressure or the middle of the foot, the vectors can actually be at an angle and not optimal alignment. An optimal alignment in the frontal plane looks something more like this. So it's going for a normal person through the center of the knee joint, or ever so slightly medial. You need to consider, though, if they are a transfemoral client or someone who is ischial bearing or ischial containing, where they're going to take that force will influence that angle of that vector as well. So, Jerry, I'm going to hand it over for some sagittal plane examples for you.
Okay.
Do you have the option of flicking ahead with these notes or not?
I don't think I can click your slides ahead, but
I'll pass you the ball.
Well, I don't know if I can control your slides.
Oh, okay. Gotcha.
I just have to ask you to advance, but.
Okay, let's go back then. All right.
Yeah, so thanks. So really a lot of what you've already explained, Aideen, is really perfectly applicable to orthotics. So when we talk about a pes equinus position, you can see what you'd have with somebody with muscular dystrophy, for instance. They are actually on the toe tips, right? And so they're in the pes equinus. So what they're trying to do is actually position the knee so they get more extension. So the L.A.S.A.R posture really shows us where that laser line is. If you could go back one, I'm sorry. I wasn't quite done. So yeah, so we see where that knee axis is, and then what we could do is actually address what the orthotic management will be. So the big thing is to know with the 3D L.A.S.A.R posture, rather than just using a plumb line would probably show us that the alignment is actually fairly correct. But why is this patient up on their toes? So we'll go to the next slide. And the reason they're on their toes is because they are trying to provide enough extension. When we are able to provide the heel, then we can see that the load line is actually progressing more to the correct position of 15 millimeters anterior to the anatomic knee axis. So that way, it's exactly what Aideen said. It validates what we've actually tried to achieve. We can go to the next one. There's a bunch of little animations. Yeah, see? Ooh.
There we go.
So then when we look at the load line, when we have plantar flexor, paresis or paralysis, then we can look at, well, now the load line is posterior to the knee axis, so that we would fall into actually uncontrolled knee flexion. So then when we go to the next slide, we know that our goal is actually to position that load line more anterior, so we can set the dorsal stop so that the load line is 15 millimeters anterior. Now, is that an earth-shaking thing that you would know to do that, to tighten the dorsal stop? No, but the thing is that each, rather than guessing like 2, 3, 4 turns, whatever, of that anterior channel, you can actually see where that knee center is and where it's optimized. The other thing too that's important is that patients change their alignment over time, just like prosthetic patients, right? So rather than blaming the device all the time, we always blame maybe post-polio patients for breaking their ankle joints, right? But really what may have happened is over time, their load line has shifted, and now we can see where we need to adjust their orthosis. We'll go to the next one. And so when we have something, plantar flexor paresis, paralysis, so now we have recurvatum, the load line is too far anterior and resulting with the compensatory position. And I'm always, in orthotics, I'm always so surprised to see how people compensate for a deficit. And of course, post-polio patients are known for this, and they maintain their stability. When we try to move them into a more a better alignment, they actually struggle a little bit because we're moving them from a position of safety and stability to maybe less stability and safety. So we'll go to the next one. So it's important what the 3D laser posture does is it gives us the opportunity to show them where their alignment should be, or as close as we can get it. So it's 15 millimeters anterior to the knee center. We can show them what their proper alignment should be, and if we can try to maybe get them into that position. Now, sometimes, granted, orthotics would be a lot easier. Actually, orthotics and prosthetics would be a lot easier for the patient, but we're able to use the laser posture to show them dynamically where they should be. We'll go to the next one. Sorry, Dean, I'm so bossy. So when we're talking about the factors for determining orthotic design, we can look at what their physiological loading is, how much should we restore them to their proper alignment. And if we're not all the way there, at least we can document where they're not. And then the non-physiologic loading, can we compensate for the muscular deficits in their relaxed standing? Can we see exactly what's happening rather than relying on the patient who often tells us what? They tell us, oh, it feels okay. Well, we don't have a lot to go on, and we're not really measuring things as scientists or biomechanical engineers. So we'll go to the next one. So when we look at positions, basically an orthotic AFO load line, we wanted about 20 to 35 millimeters anterior to the knee pivot. And you'll notice there's quite a bit of play because we're trying to address where the patient feels most comfortable. But if we have an offset knee joint, as you would predict, it's 40 to 60 millimeters anterior because we already have that stability built into the design of the KFO. On again to the next one. So even when we can even use 3D laser posture when the patient really can't bear much load, and we can see the effect of an assistive device. So go to the next one. So when we position them where they should be, we can arrange things so we can see exactly where that 3D laser posture. Now, I have to admit, I guess I have to say, am I becoming an old timer? Maybe. We used to use plumb lines for RGOs, right? Well, I could use a plumb line and tell if that patient was more or less the centers of the axes were positioned, but I didn't know where the load line was. And so I was really kind of guessing with the 3D laser posture. There's no more guessing where the load line is, and I can position that dorsal stop and actually get a much more tuned orthosis for where they're at in their, in their rehabilitation. Next one, please. And so when we see someone with a knee extensor deficit, and these are people we would maybe use a C brace or free walk or EMAG, I can see where the posterior stop of the ankle joint, so the load line is 40 to 60 millimeters anterior. So we can actually set that. So we'll go to the next one, Dean. So see, I can actually position that into the right spot. Now, sometimes the patient honestly resists this, right? But we can try to achieve it. And then if we have an extensor chain, where we have the plantar flexors, quads, and hip extensors, we can set the knee angle so that the load line is 15 millimeters in front of the knee joint. If we don't do this, we might actually create too much of a bind at the and knee joint. Unfortunately, we used to just kind of blame the orthosis, right? I mean, it's convenient, it's tangible. We could just say, well, Ottobock or whatever manufacturer provided poor knee joints, right? But what we could actually see is like, oh, wait a minute, the load line is so far posterior. That's why we keep breaking the joints. Next one, please. And so what we have to do is try to find a position where they're more in stability, where we adjust the ankle joint, and maybe we won't have this break. So we'll go to the next one. So in the frontal plane, the same thing is true. We can look at genuvarum or valgum. Aideen's actually kind of already explained this. Using 3-point pressure, we can actually see where the proper position is. And, maybe the patient won't accept where it should be, but they'll actually be able to experience where proper alignment is, and we can see how close we can get them and also document where they're at in time so that maybe we can slowly creep up onto where the proper alignment is, or at least we know how far off we are. So it should be about 20 millimeters lateral to the knee center or bisection of the patella. This also helps us set corrective wedging, right? A lot of times we'll just kind of guess based on our qualitative knowledge of orthoses, but if we can place the wedge, we can actually see what the effect has been rather than asking the patient, oh, what do you think of that? And normally they just kind of say, well, I don't know, it's different. But now we can actually see, well, okay, well, that's exactly where we need to be. Okay, the next one, please. Yeah, we can do a medial wedge or a lateral wedge and really establish that well. So before we move on from orthotics, there's 3 main things. It really answers the question, why are the orthotic braces breaking? And then how has the alignment changed over time? And how do we capture that? And how do we have the patient approximate or have knowledge of what the proper alignment should be? And then the last one is documenting that for the future. And that's your orthotic interlude, Aideen.
Thank you, Jerry. And that is exactly what I wanted to touch on next, is that documentation. So I think, I mentioned it before, but I absolutely love what this is able to do for us. So if you can see this screen here, it was a Meridium trial that I was part of. We had the patient standing on the force plate. I took a snapshot of our initial bench alignment. So you can see a little bit posterior on that prosthetic side, and you can see I've written here before optimization, and then I just snuck a little bit of plantar flexion in, and then we have 2 nice little lines here, and that was after optimization. So the L.A.S.A.R posture allows you to create a PDF or photo files and things like that, and export it out as emails or into data station or into your own patient documentation. So I think that's really critical for sort of the age that we're in now, where we need to document our interventions. So just a really small summary that the 3D L.A.S.A.R posture is really taking us into, that modern day approach. We call the old L.A.S.A.R posture outdated. Yes, it is 20 years old, but it's still very, very valuable. But I really enjoy the extra features of the 3D L.A.S.A.R posture. I like the way it's transportable. I personally carry a L.A.S.A.R posture with me every week on aeroplanes. And so I can attest that it is transportable. We are showing the real-time ground reaction force. So it's a real live display, which is fantastic. It gives us that overall ground reaction force, not just the vertical. And we can also see both the right and the left leg at the same time. So a lot of extra additional value as well. Finally, just a huge thank you to our colleagues from around the world that have all contributed to this technology and shared some really nice images for this presentation. So a big shout out to them: Martin Push, Malte Bellman, Dries Glorier, Christian Reitinger, and of course my own colleagues here in the US and the PCS team as well.
Thank you for watching this previously recorded Experts on Demand webinar by Ottobock. Please click the link in the video description to access the quiz and submit for continuing education credit. If you have any questions, please contact the education team at 1-800-328-4058 or via email at us.education@ottobock.com.